In this video, we'll be talking more about strain gauges, particularly how they're made and how they're actually used and applied. So here's a zoomed in version of a strain gauge. And essentially what you see is a sensing element where you've got a whole lot of almost parallel lines. And then you've got a few other things, some spots where you can solder some wires to, sometimes some arrows there so you can work out the orientation of the strain gauge. And essentially you want to measure force along the axis of where those parallel lines are. So you're measuring this way and you're measuring deformation that way. You're not measuring it this way. So that's the way that we orientate our strain gauge as our sensor element. Now, how do they actually work? Well, essentially we have a fine piece of foil. We put it over a resin base and we photo etch. We etch away the parts that we don't want. So you see all those almost parallel lines. In between those parallel lines, we etch away parts and get rid of them. We then take that resin base that the foil's attached to, and we affix it to something. We've got a video later on where we talk about different bonding mechanisms, how we can affix it to something, but we want to affix to something so that as that material moves, our gauge actually moves as well. It's strongly affixed there. Now, I mentioned we want to orientate our gauge the right way. And if you think about this as a gauge, it's not, it's a business card. But if you think about it, you've got these long lines here, which are our sensing element. And we want them so that it's going to bend in this direction like this. If it bends in this direction, the actual change in resistance is not going to be very much because we've got very little amount of width in this regard. Most of it is here. And so we might get a tiny, tiny, tiny change in resistance along this axis here. But by far, our biggest change in resistance is going to happen when this deforms here. And so I mentioned we want to bond that somehow to our different thing that we're trying to measure. And we've got different ways of bonding depending on what we'll be measuring. Now, for example, if we're bonding it to concrete versus bonding it to a steel beam, we've got different materials and different things we can apply to actually perform that bonding process. You can see here though that at some point we need to solder some wires to it. So there's some pads on there that allow us to solder our wires to that gauge, and those wires will go off to our measurement device and allow us to read what's going on. And as we've said before, as we stretch that beam or we deform that beam along the measurement axis of our strain gauge, our resistance can change. And so we actually connect some sort of device for measuring resistance, we'll talk about that soon, to our strain gauge, and that allows us to work out how has that resistance actually changed and infer how much strain our beam is under. Let's look at some typical values for a typical small strain gauge. Our gauge factor, particularly for those nichrome ones we talked about before, will be about 2 to 2.2, something in that sort of range. And our resistance, when we haven't strained it, when it's unstrained, is 120 ohms. Now, there are different strain gauges at 350 ohms and 700 ohms and a kilo ohm, for example. This is one very standard and commonly used one. They're quite linear, so within plus or minus 0.3%. And you can see there the maximum strain that they can measure under compression and under tension. So not very much. We're not going to be bending these things back on themselves like this. It's actually quite a small amount of strain that's being measured. And you can also see there that, remember, our unstrained resistance is about 120 ohms. You can see the amount at that maximum value of tension and compression, the amount of strain that we're actually measuring there in resistance, 4.8 ohms or minus 2.4 ohms. One of the nice things about that is we can determine whether it's under tension or compression based on whether it's a positive or negative resistance change that we've got there. And our operating temperatures for a gauge like this, something like 150 degrees, but these vary from gauge to gauge. So one thing that's becoming clear is what we're doing with the strain gauge is we're converting that strain into resistance, and that resistance is quite small. That change in resistance is quite small, something in the order of less than 10 ohms for a full scale from maximum compression to maximum tension. That's quite small, so how do we actually measure it? Well, there are a number of different ways we can measure it. We're going to go into this in not a huge amount of detail, and we're not going to go through all the derivations of it because it's not primarily an electrical course. We're teaching you essentially how to use these things and interpret data from them. But we need to understand a bit about some of the errors that can occur depending on how we actually measure these. Now, probably the simplest way of measuring a resistance is to put together a voltage divider circuit. Now, you guys did these in first year in IAL. And essentially a voltage divider circuit, you have two resistors, you put a voltage across those resistors, and the voltage between those resistors, marked at V out or voltage out in this particular circuit above, will change depending on the relative value of those resistors to one another. So for example, we could have a fixed resistor at the bottom there, and we could put our strain gauge there at the top. And based on how that strain gauge changes at the top, our voltage output will change. So if our voltage, if our resistance changes and goes up a bit, our voltage will change by a proportional amount to how much the other one changes. And we have the voltage divider rule that tells us, based on what the relationship between the voltage supply is and the ratio of the R1 to R2, tells us what our voltage output will be. And we can calculate that very clearly. Now, we feed that into the analog to digital converter of a little microcontroller or a separate analog to digital converter, and that will give us our voltage in a digital format. Having said that though, environmental factors will actually change these measurements. And one of the significant environmental factors that's going to change the measurements is temperature, because our resistivity changes with temperature. We looked at a chart earlier on for different materials, how much that resistivity will change. And it can be quite significant. So this isn't really a very good solution because maybe our device isn't under strain, but the temperature's changed significantly. And now our circuit thinks, we're under strain because our resistance has increased from our strain gauge. And it hasn't. The temperature's been the thing that's changed. The other thing here is our resistance is only changing by a tiny amount. And so our voltage across that voltage divider will only change by a tiny amount as well. So let's look at a different way of doing this and a better way of doing this. There's the Wheatstone bridge. Now, the Wheatstone bridge is quite old. 1833, it was developed. It was popularized by Sir Charles Wheatstone, who it's named after, in 1843, 10 years later. And this allows us to do extremely accurate measures of small resistances, small changes in resistance. And basically it involves two balanced bridges, and balancing out the voltages between these two bridges. If one of the resistors in there changes, we can see a change in the voltage between those two bridges. And so our element there, VG, which is in the middle there, is something that we use to measure our voltage. And that voltage will change based on the resistance, one of those resistances in the legs changing. Now, once again, we're not going to go through all the derivations of this, how it actually works. But essentially what we want to do is we say Rx is our unknown resistance. That might be, in our case, our strain gauge. And what we want to do is say R2, the resistance on the bridge across from it, is a variable resistor, one of those ones that we can change with a little screwdriver. And what we want to do is tune them in so that when that strain gauge is at rest, they'll be about the same. When they're about the same, the voltage between, assuming that R1 and R3 are pretty well matched, the voltage at VG, or the voltage between D and B, is 0 volts. And so our ratio between R2 over R1 should be equal to our ratio of Rx over R3. And so as our Rx changes, our voltage will change. And so our most basic form of using a Wheatstone bridge to measure our strain would be putting our strain gauge at Rx, tuning in R2 to be exactly the same value as Rx. And we can do that with a multimeter. We just measure what the voltage is there. What we then do is put this through a little amplifier because our voltages here are quite small. That amplifier will boost it up, and then we'll see a bigger change in voltage as different amounts of strain are applied to that strain gauge. Now, we still have a problem with this. And our problem is that we still have these temperature issues that may occur. We're not compensating for temperature. And so that resistance from the strain gauge may increase or decrease depending on whether the temperature increases or decreases. And we'll think that our voltage will be going up or down. We'll think that it'll be under strain. We don't want that. And so one thing that we can do is use a half bridge approach. And here we have two strain gauges. We have a reference strain gauge and the strain gauge we're trying to measure and the dimension that we're trying to measure. And the interesting thing here is that that reference strain gauge, the resistance of that strain gauge will go up and down as the temperature goes up and down exactly the same way, if they're right next to each other, as the other strain gauge. And so you see our picture above, we have our reference strain gauge perpendicular to the strain gauge we're trying to measure. And the strain in that reference strain gauge shouldn't increase or decrease with deformation of the material. It should only really increase or decrease with those environmental conditions, like our temperature changes. And what's happening here is we're essentially negating the effect of that temperature change by putting it in our strain gauge there. Now, we're not limited just to 2 strain gauges in our device. We can have more strain gauges. And we can have some of those strain gauges along the axis we want to measure, and some of those strain gauges as reference ones. And that will allow us to negate effects for things like temperature, but will also allow us to amplify any strain that we're having, that we're actually trying to measure. And amplifying that strain will make it easier to measure and more immune to things like noise and drift. And so we see in our picture here, when we've got just our our quarter bridge implementation, we have a fair bit of error happening there and a fair bit of, we've got a bit of a curve happening. When we move to a 4-element Wheatstone bridge with 4 strain gauges there, we manage to correct for most of that and have quite a straight line.